Good morning everyone. I am Vanshaj from BSc Chemistry Honors 3rd year. In this audio lecture for visually impaired session, I have prepared a audio lecture on quantum mechanics 2 which was taken from the book Pradeep's Physical Chemistry volume 3rd by Dr. S.C. Kheterpal. Now starts quantum mechanics 2nd. First, introduction. The formation of covalent bond was explained for the first time by Jean Lewis in 1916. He suggested that a covalent bond between two atoms was formed by sharing of electrons between the atoms so as to complete their octets and acquire stable configuration. Further, when the atom approaches each other, there are new forces of interaction, attraction and repulsion between the electrons and the nuclei. The force of attraction being greater than the force of repulsion result into lowering of energy. The internuclear distance at which the system has minimum energy, the stability is maximum. This distance is called the bond length. Lewis' concept could explain the stability of the molecules and that too only qualitatively. It could not answer some of the basic questions as follows. First, why do atoms combine to form molecules in some cases but not in others? Example, H2 is stable but helium 2 is not. Second question arises is why only certain combinations are possible but not other. Example, hydrogen and oxygen combine to form H2O and H2O2 but not H2O3. Third question, why different bonds have different bond energies? Fourth question, why molecules have different shapes? Example, CO2 is linear while SO2 is a bent molecule. Fourth question is why molecules have different shapes. Example, CO2 is linear while SO2 is a bent molecule. The answers to the above questions have been provided quantitatively by quantum mechanics by applying Schrödinger wave equation to calculate the properties of the system consisting of nuclei and electron. The following two different approaches have been put forward. First, valence bond theory. Second, molecular orbital theory. The simplest system to be studied was hydrogen molecular ion H2 positive as it consisted of only two protons and one electron. However, even for such a simple species consisting of three interacting particles, no exact solution of Schrödinger wave equation is possible in classical mechanics as well as quantum mechanics. Hence, in applying Schrödinger wave equation to even simple molecules or ions, certain approximations are made. One of the most important is Born-Oppenheimer approximation as explained in the next section. Now, Born-Oppenheimer approximation. According to this approximation, it is supposed that the nuclei being thousands of times heavier than an electron move relatively very slowly and may be treated as stationary while the electron moves with a higher speed relatively to nuclei. For example, calculations suggest that nuclei in S2 vibrate through only 1 pm whereas electron move with speed of order of 1000 pm. So the error of assuming that the nuclei are stationary is negligible. Taking the example of H2 positive ion, if the nuclei of the two atoms are represented as HA and HB, then in view of Born-Oppenheimer approximation, the distance between the nuclei may be fixed at an arbitrary value r and Schrödinger wave equation may be solved for the wave function of the electron which is at distance Ra from nucleus Ha and at a distance Rb from nucleus Hb. This in this calculation R is held constant and only Ra and Rb are varied. Now a new value of R is chosen and the calculation repeated and so on. This internuclear R is a constant parameter in one calculation. When the calculations have been done for a number of values of R, the energy ER of the system may be plotted against R. The curve obtained for H2 positive is shown in figure 2.2. It is called potential energy curve because the kinetic energy of the nuclei is zero. From the curve thus obtained from the theoretical calculation, the equilibrium bond length Re and bond dissociation energy dE can be obtained from the minimum of the plot. These can be compared with experimentally observed value. For example, for H2 positive ion, the observed values of bond dissociation energy and equilibrium bond distance have been found to be 2.78 electron volt and 1.06 angstrom respectively. The calculation of potential energy of H2 positive ion is described in the next section. Now next section, calculation of energy from wave functions. The Schrodinger wave equation in the operator form is H psi equal to E psi. Multiplying both sides of the equation with psi star and integrating over the whole space, we get integrating of psi star H cap psi d tau limit minus infinity to plus infinity equals to psi star E psi d tau integrating limit minus psi to plus psi. As E is constant, the above equation can be rewritten as psi star h cap psi d tau integrating minus infinity to plus infinity equal to E integrating minus infinity to plus infinity psi star psi d tau, or E equals to integrating minus infinity to plus infinity psi star h cap psi d tau by integrating minus infinity to plus infinity psi star psi d tau. This one is third equation. If psi is a real function, equation 3 can be rewritten as E equals to integrating minus infinity to plus infinity psi h cap psi d tau by integrating minus infinity to plus infinity limit psi square d tau. The Hamiltonian operator h cap is given by h cap equals to minus h square by 8 pi square m delta square plus v, where delta square is a Laplacian operator which is a function of coordinate x, y, z of the electron. Thus, to obtain the value of E for the given system, we substitute the value of potential energy of the system and should know the correct value of the wave function. In case of hydrogen atom, there is only one proton and one electron. Hence, its potential energy is minus E square by R. In case of molecules or ions, potential energy has to be calculated from the different interaction between the electrons and the nuclei. Moreover, in case of hydrogen atom, only one Laplacian operator is involved for the only electron present, but for species containing more than one electron, Laplacian operator is required for each of the electron. Two simple cases are described below. First case, hydrogen molecular ion H2 positive. Although the charged species H2 positive cannot be isolated, it is found to be present in high concentration when electric discharge is passed through the discharge tube containing H2 gas. This species consists of two protons and one electron. As shown in figure 2.1, if the two protons are represented by HA and HB and the distance between them is kept fixed at R, Born-Oppenheimer approximation, and for one particular position the electron is at distance Ra from proton Ha and at distance Rb from proton Hb, then potential energy of the system is the sum of different electrostatic potential energy found by applying Coulomb's law as under. For electron proton Ha intersection, V1 equals to E square by में Ra. Negative. For electron proton Hb interaction, V2 equals to minus E square by Rb. For two protons separated by distance r, V3 equals to E square by r. Hence, total potential energy of S2 positive for the given arrangement of charges will be V equal to V1 plus V2 plus V3 equals to minus E square by Ra minus E square Rb plus E square by R. This one is the sixth equation. Thus, Hamiltonian operator for the system is h cap equals to minus h square by 8 pi square m delta square minus e square by Ra minus e square by Rb plus e square by R. Consequently, Schrodinger wave equation for H2 positive ion is S psi equal to E psi, that is minus h square by 8 pi square m delta square minus e square by Ra minus e square by Rb plus e square by R into psi equals to E psi. This one is the eighth equation. Now second case is hydrogen molecule H2. Hydrogen molecule H2 contains two protons and two electrons. For one particular distance r between the two protons and for one particular position of the two electrons, different distances are represented in figure 2.3. The potential energy of the molecule will be V equals to E square by Ra1 minus E square by Ra2 minus E square by Rb1 minus E square by Rb2 plus E square by R12 plus E square by R. This one is the ninth equation. The Hamiltonian operator will be h cap equals to minus h square by 8 pi square m in bracket delta 1 square plus delta 2 square plus v. This one is the 10th equation where delta 1 square and delta 2 square are all the Laplacian operators referring to the coordinate of two electrons. Consequently, the Schrodinger wave equation for H2 molecule will be H psi barabar equals to E psi, that is minus h square by 8 pi square m in bracket delta square plus delta 2 square plus v into psi equals to E psi. This one is the 11th equation where psi is the total wave function of the two systems in the molecule. The most important quantity that will still remains to be found to obtain the value of total energy E of the system is correct value of the wave function psi. If we do not know psi, V of the system is the incorrect value of the wave function. If we do not know psi, we selected by a method known as variation method or Reed's linear combination method as described below. Variation method to obtain the correct wave function. We guess some approximate wave function psi1 on the basis of our knowledge of possible electron distribution and then calculate energy E1 according to the equation. E1 equals to minus infinity to plus infinity limit psi1 h cap psi1 d tau by integrating minus infinity to plus infinity upper limit psi1 square d tau. This one is the 12th equation. Similarly, if we try a number of wave function psi2, psi3, etc. by considering different possible electron distribution and calculate the corresponding energy E2, E3, etc. Then according to variation principle, the following results are observed. The energy E1, E2, E3, etc. will always be greater than the value of true energy E. The trial wave function which gives the lowest value of energy is closest to the true wave function. Similarly, the lowest value of energy will be closer to be true energy. Reed's linear combination method. This is also based on variation method. According to this method, the trial wave function for the diatomic molecule is taken as a linear combination of two wave function. Example, in H2, the two wave function are of 1s orbitals. Thus, in general, if the two wave function combining linearly are psi1 and psi2, then the trial wave function is taken as psi equals to c1 psi1 plus c2 psi2, which is the 13th equation, where c1 and c2 are the coefficients which can be varied. Substituting this value of the wave function in equation number 4, the energy is calculated, that is, we have E equals to integrating minus infinity to plus infinity in bracket C1 psi 1 plus C2 psi 2 H cap in bracket C1 psi 1 plus C2 psi 2 d tau by integrating minus infinity to plus infinity upper limit in bracket C1 psi 1 plus C2 psi 2 square d tau. This one is the 14th equation. Now the coefficients C1 and C2 are varied to find out the wave function psi, corresponding to which the energy comes out to be minimum. The condition for getting the minimum of energy with respect to the coefficients C1 and C2 is that we carry out partial differentiation of equation number 14 with respect to C1 and C2 and put the result equals to 0. That is, del E by del C1 equals to 0 and del E by del C2 equals to 0. Combining different results, we get a quadratic equation in E, which contains the coefficients C1 and C2. These can be solved to get the value of E, C1 and C2, discussed later in section 2.5.2. Similarly, if the trial wave function psi is a linear combination of a number of wave function psi1, psi2, psi3 etc. with coefficient c1, c2, c3 etc. we take the trial wave function as psi equals to c1 psi1 plus c2 psi2 plus c3 psi3 plus dot dot dot. The coefficients are then calculated by variation method to get the wave function which is the closest to the correct wave function, which will give minimum value of energy. The advantage of this method is that if any wrong function is included in the expression for the trial wave function, the coefficient of the wave function will automatically comes out to be 0. As mentioned in the beginning, there are two approaches to explain the nature of chemical bonding and to predict the properties of molecules such as bond distance, bond dissociation energy, dipole moment, etc. These are valence bond theory and molecular orbital theory. The two theories mainly differ in the fact that whereas according to VBT, atoms are considered to retain their identity, and bond is formed as a result of interaction of only the valence electrons of the atoms. On the other hand, MOT considers the molecule as a collection of nuclei and all the protons of the molecules are distributed in different energy levels around the group of nuclei, just as the electron of an atom are distributed in different energy levels of a single nucleus. Just as energy level of an atoms are called atomic orbitals, the energy level of the molecule are called molecular orbitals. Thus, according to MOT, all the atomic orbitals of an atom overlap with the appropriate atomic orbitals of the other atom. Unlike VBT, where only half-filled valence atom orbitals overlap. Now, 2.4 Valence bond theory. This was the first quantitative theory based on quantum mechanics that was used to calculate the energy of S2 molecules. It was put forward by Hitler and London in 1927 and was further extended by Slater and Pauling. Before we discuss these theories, some basic quantum mechanical principles involved in the theory are given below. The total wave function psi of the two independent systems with wave function psi a and psi b is equal to their product. That is, it is given by psi equals to psi a into psi b. The total energy of the two independent systems with energy EA and EB equal to their sum. E equals to EA plus EB. The total Hamiltonian is also equal to the sum of their value for independent system, that is H dash equals to H cap A plus HB cap. This one is the third equation. For many electron system, the total wave function is a linear combination of different wave function involved, that is psi equals to C1 psi 1 plus C2 psi 2 plus dash dash dash. This one is the fourth equation where coefficients C1 and C2 etc. are found by variation method so that psi is closest to the true wave function corresponding to which the energy of the system is minimum. Fifth point, the square of the coefficient of any function gives the contribution of that wave function towards total wave function and is usually called the weight of that wave function. For this function psi is to be normalized, the following condition must be satisfied. C1 square plus C2 square plus C3 square equals to 1. This one is the fifth equation. Now let us apply valence bond theory to the study of bond formation in S2 molecule. Application of valence bond theory to study of S2 molecule. Let us start with two hydrogen atoms separated by a large distance so that there are no force of interaction between them and the energy of the system is taken as 0. Let the two H atoms be represented by HA and HB and the electron associated with them by E1 and E2 respectively. That is, the two H atoms may be represented as HA E1 and HB into E2. Also suppose the wave function associated with these electrons are represented by psi A1, psi B2 respectively. Hence the total wave function for the two separated hydrogen atom will be given by psi equals to psi A1, psi B2. Now if the atom are brought close together and for each distance between the two atom, potential energy is calculated according to equation 9 section 2.3, and then the total energy of the system is calculated by substituting the value of psi from equation number 6 above in equation number 4 section 2.3. We have E equals to integrating limit minus infinity to plus infinity psi a into 1 psi b into 2 h cap psi a into 1 psi b into 2 d tau by integrating the limit minus infinity plus infinity psi a into 1 psi b into 2 square d tau. This one is the required seventh equation. If the value of E is plotted as a function of intermolecular distance, curve I is obtained as shown in figure 2.4. It may be seen that energy of the system decreases with distance till a minimum is reached. This represents the formation of H2 molecules. The decrease in energy corresponding to this minimum represents the bond energy and the distance represents the bond length. However, this curve has been obtained by using the wave function as represented by equation 6. The bond energy is found to be only 24 kJ per mole, which is much lower than the actual experimental value of 458 kJ per mole. Similarly, bond distance is found to be 90 pm, which is much different from the actual bond length of H2 molecule with 74 pm. This shows that the wave function used in the above calculation with psi a into 1 psi b into 2 is not a good approximation. Hence, some other interaction between the two hydrogen atoms will have to be taken into consideration to arrive at a better wave function. The different possible interactions are described below. Exchange of electrons. In writing the above wave function, it was assumed that the electrons are distinguishable, that is, electron E1 belongs to HA and E2 belongs to HB. However, as the electrons are actually indistinguishable after the overlap of two atomic orbitals, electron E1 may be under the influence of nucleus of HB and also electron E2 may be under the influence of HA. Thus the system may consist in two different states as follows: HA into E1 HB into E2, second HA into E2 HB into E1. This one is a required equation. The wave function corresponding to these two states may be written as psi1 equal to psi A into 1 psi B into 2. Second wave function psi A into 2 psi B into 1. This is the ninth equation. The total wave function of the system will be a linear combination of above two functions. For S2 molecule, as both atoms are same, put C1 equal to C2 equals to 1. Hence, psi VB equals to psi A into 1 psi B into 2 plus minus psi A to psi B1. This is the 11th equation. There are two possible linear combinations of the wave function corresponding to which the wave function may be represented by psi positive and psi negative, that is in 12th and 13th equation. If the energy are calculated as a function of internuclear distance by employing the wave function psi negative, the curve second is obtained, which shows that energy increases when the atoms are brought closer together. Thus, it does not lead to bonding and represent a non-bonding state. On the other hand, if energy is calculated as a function of internuclear distance by using the wave function psi positive, curve third is obtained. It represents decrease of energy with minimum at a particular distance and represent a bonding state. It is interesting to note that through equation 8 represent two different states, but charge distribution on the two nuclei is same in both cases. That is, each of them represent a state of covalent bond. That is why the wave function psi positive is sometimes called the covalent wave function and may be represented as psi covalent. Using this equation, the minimum in the curve is found to be 303 kJ per mole, and at a nuclear distance of 80 pm, thus both the values have come closer to the experimental value. The extra lowering of energy that has been observed due to taking into consideration the change of electron between the two hydrogen atoms is called exchange energy. Thus, exchange energy of H2 molecule equals to 303 minus 24, we get 279 kilojoule per mole. Second one is the screening effect of electrons. When the atoms come closer together, the electron of one atom shields the electron of other atom from the nucleus. The electron does not feel full interaction by the nucleus. In other words, its effective nuclear charge is less than the actual nuclear charge. Taking this fact into consideration, the wave function was further improved. Using this wave function, energy versus internuclear distance curve obtained is shown at figure 4 2.4. The minimum in this curve lies at 365 kJ per mole, which shows a further improvement in the value. Now, third case, ionic structure of S2 molecules. Since the calculated value of 365 kJ per mole is still quite low as compared to the experimental value of 458 kJ per mole. Further improvement in the wave function is required by taking more interactions into consideration. It was suggested that when the atoms come close together, both the electron may lie close to nucleus HA or close to HB, giving rise to two possible ionic structures as follows. Thus, the possibility of existence of these states is a very little because Coulombic repulsion between the electron will be much larger than the attraction between HA negative, HB positive or HA positive or HB negative. Yet, by taking these structures into consideration, wave function could be further improved. The wave function corresponding to state third and fourth may be written as psi third equal to psi a into 1, psi a into 2, psi 4 equal to psi b into 1, psi b into 2. This is the 15th equation. Now, combining the covalent and ionic wave function, the complete wave function for the system may be written as psi equal to psi covalent plus psi ionic. We get where Lambda gives the extent of contribution of the ionic structures toward bonding and is usually called the mixing coefficient. Its value for S2 is found to be 0.17. Further improvement in wave function have been done but still will be discussed here. It is important to mention that valence bond theory led to the concept that a molecule or ion may consist in different structure, none of which represent the actual structure, and the actual structure is in between the different structure. This phenomena is called resonance and the different structure are called resonating structure. The actual structure is more stable than any of the resonating structure. Thus the concept of resonance follows from VBT. This is from my side. Thank you and have a nice day.